Okay, we're starting a new chapter. This is chapter 7 on the Fourier Transform, which I will often abbreviate as FT, and we'll start with the definition of the Fourier Transform of a time domain signal. It's the integral from minus infinity to infinity of x of t times e to the minus j omega t integrating over all time. So this is the Fourier transform. And then we can also calculate the inverse Fourier transform. It's 1 over 2 pi integral from minus infinity to infinity of x of omega e to the positive j omega t integrating over all omega. This is the inverse Fourier transform. Notice, unlike with the Laplace transform, which involved a contour integration to do the inverse Laplace transform, we can calculate an inverse Fourier transform with just a regular integration. But we will still have a table of transforms that we will refer to quite frequently. Some other notation that you may see: x of t transforming to x of omega. Again, the convention we'll use if a lowercase x represents the time domain signal, a capital X would represent the Fourier transform. You might also see this written slightly differently. You might see x of omega written as the Fourier transform. So this is a script f of x of t, or you might see x of t written as, again, the script f to the minus 1 to remind you of the inverse of x of omega. Okay. X of omega may also be called the spectrum of x of t. So we'll be dealing with the Fourier transform of signals, and again, the Fourier transform of a signal may also be called the spectrum of the signal. We'll also talk about the Fourier transform of the impulse response. That gives us the frequency response, which we can break down into the magnitude response and the phase response. So again, we'll use the term spectrum for Fourier transform of signals, and the term response for the Fourier transform of an impulse response when we're talking about systems. So again, x of omega is a complex function of omega, so we can write it in exponential form as the magnitude of x of omega times e to the j angle of x of omega. And x of omega is called the magnitude spectrum of x of t, and angle here of x omega is called the phase spectrum. So we can use the definition of the Fourier transform to calculate the Fourier transform of a couple of simple functions. So let's first find the Fourier transform of x of t is e to the minus at u of t. So a causal decaying exponential directly from the definition of the Fourier transform. We'll have the integral from minus infinity to infinity of e to the minus at u of t, and then e to the minus j omega t dt. So because of the unit step function here, our lower limit reduces to 0, and then we can combine the two exponents and have a plus j omega t dt, and carrying out that integration, I'll get minus 1 over a plus j omega e to the minus a plus j omega t evaluated at my limits, my integration limits. This will become, assuming a is greater than 0, and I evaluate that at t equal to infinity, this exponential will decay to 0, and so this will reduce to 1 over a plus j omega, again as long as a is greater than 0, or in which case we have a decaying exponential. So we can sketch, again, this is our result. X of omega is 1 over a plus j omega. Magnitude spectrum is then magnitude of the numerator is 1, magnitude of the denominator is a squared plus omega squared. And similarly, the phase spectrum of the signal is the angle of the numerator is 0. I'll have minus the inverse tangent of the imaginary part over the real part. And so I can sketch those. X of omega as a function of omega. Again, this is an entirely real function. You can find it at omega equal to 0, it's going to be 1 over the square root of a squared, or 1 over a. And then we can also find it at another convenient point is at omega equal to a. I'll have then 1 over the square root of a squared plus a squared, or 1 over the square root of 2 times a. So this is 1 over a, and then here the response will be down 1 over the square root of 2 times that. The response will look something like this, and then continue to decay away to 0. And this is symmetric since omega appears here as omega squared in the function. So this would be a symmetric function, have even symmetry. And then the phase spectra as a function of omega at omega equal to 0. This is 0 at omega equal to a. Get the inverse tangent then of 1 for 45 degrees. So minus 45 degrees there. As omega continues to increase, this will approach negative 90 degrees for positive frequencies. So the phase response is going to go through that point and then approach 90 degrees. Our phase response actually has odd symmetry, so it'll look like this as we go back toward negative frequencies, plus 90, and then at minus a, again it will be 45 degrees, plus 45 degrees. This is what the phase spectrum of X omega looks like. In this particular case, the Fourier transform only exists for a decaying exponential. We can show in general that the Fourier transform exists if the time domain function is absolutely integrable, which means that if we integrate the absolute value of x of t, we get a finite result. If that's the case, then x of t has a Fourier transform.